Chapter 3. High-Speed Aerodynamics. Developments in aircraft and power plants have produced high-performance airplanes with capabilities for very high-speed flight. The study of aerodynamics at these very high flight speeds has many significant differences from the study of classical low-speed aerodynamics. Therefore, it is quite necessary that the naval aviator be familiar with the nature of high-speed airflow and the characteristics of high-performance airplane configurations. General concepts and supersonic flow patterns. Nature of compressibility. At low flight speeds, the study of aerodynamics is greatly simplified by the fact that air may experience relatively small changes in pressure with only negligible changes in density. This airflow is termed incompressible, since the air may undergo changes in pressure without apparent changes in density. Such a condition of airflow is analogous to the flow of water, hydraulic fluid, or any other incompressible fluid. However, at high flight speeds, the pressure changes that take place are quite large, and significant changes in air density occur. The study of airflow at high speeds must account for these changes in air density, and must consider that the air is compressible and that there will be compressibility effects. A factor of great importance in the study of high-speed airflow is the speed of sound. The speed of sound is the rate at which small pressure disturbances will be propagated through the air, and this propagation speed is solely a function of air temperature. As an object moves through the air, mass, velocity, and pressure changes occur which create pressure disturbances in the airflow surrounding the object. Of course, these pressure disturbances are propagated through the air at the speed of sound. If the object is traveling at low speed, the pressure disturbances are propagated ahead of the object, and the airflow immediately ahead of the object is influenced by the pressure field on the object. Actually, these pressure disturbances are transmitted in all directions, and extend indefinitely in all directions. Evidence of this pressure warning is seen in the typical subsonic flow pattern of Figure 3.1, where there is upwash and flow direction change well ahead of the leading edge. If the object is traveling at some speed above the speed of sound, the airflow ahead of the object will not be influenced by the pressure field on the object, since pressure disturbances cannot be propagated ahead of the object. Thus, as the flight speed nears the speed of sound, a compression wave will form at the leading edge, and all changes in velocity and pressure will take place quite sharply and suddenly. The airflow ahead of the object is not influenced until the air particles are suddenly forced out of the way by the concentrated pressure wave set up by the object. Evidence of this phenomenon is seen in the typical supersonic flow pattern of Figure 3.1. The analogy of surface waves on the water may help clarify these phenomena. Since a surface wave is simply the propagation of a pressure disturbance, a ship moving at a speed much less than the wave speed will not form a bow wave. As the ship's speed nears the wave propagation speed, the bow wave will form and become stronger as speed is increased beyond the wave speed. At this point, it should become apparent that all compressibility effects depend upon the relationship of airspeed to the speed of sound. The term used to describe this relationship is the Mach number, m, and this term is the ratio of the true airspeed to the speed of sound. m equals v over a, where m equals Mach number, v equals true airspeed in knots, a equals speed of sound in knots, or a equals a naught times the square root of lowercase theta. A naught equals the speed of sound at standard sea level conditions, 661 knots, lowercase theta equals temperature ratio, or T over T naught. It is important to note that compressibility effects are not limited to flight speeds at and above the speed of sound. Since any aircraft will have some aerodynamic shape and will be developing lift, there will be local flow velocities on the surfaces which are greater than the flight speed. Thus, an aircraft can experience compressibility effects at flight speeds well below the speed of sound. Since there is the possibility of having both subsonic and supersonic flows existing on the aircraft, it is convenient to define certain regimes of flight. These regimes are defined approximately as follows. Subsonic, Mach numbers below 0.75. Transonic, Mach numbers from 0.75 to 1.20. Supersonic, Mach numbers from 1.20 to 5.00. Hypersonic, Mach numbers above 5.00. While the flight Mach numbers used to define these regimes of flight are quite approximate, it is important to appreciate the types of flow existing in each area. In the subsonic regime, it is most likely that pure subsonic airflow exists on all parts of the aircraft. In the transonic regime, it is very probable that flow on the aircraft components may be partly subsonic and partly supersonic. The supersonic and hypersonic flight regimes will provide definite supersonic flow velocities on all parts of the aircraft. Of course, in supersonic flight, there will be some portions of the boundary layer which are subsonic, but the predominating flow is still supersonic. The principal differences between subsonic and supersonic flow are due to the compressibility of the supersonic flow. Thus, any change of velocity or pressure of a supersonic flow will produce a related change of density, which must be considered and accounted for. Figure 3.2 provides a comparison of incompressible and compressible flow through a closed tube. Of course, the condition of continuity must exist in the flow through the closed tube. The mass flow at any station along the tube is constant. This qualification must exist in both compressible and incompressible cases. The example of subsonic, incompressible flow is simplified by the fact that the density of flow is constant throughout the tube. Thus, as the flow approaches a constriction, and the streamlines converge, velocity increases and static pressure decreases. In other words, a convergence of the tube requires an increasing velocity to accommodate the continuity of flow. Also, as the subsonic incompressible flow enters a diverging section of the tube, velocity decreases and static pressure increases, but density remains unchanged. The behavior of subsonic incompressible flow is that a convergence causes expansion, decreasing pressure, while a divergence causes compression, increasing pressure. The example of supersonic compressible flow is complicated by the fact that the variations of flow density are related to the changes in velocity and static pressure. The behavior of supersonic compressible flow is that a convergence causes compression while a divergence causes expansion. Thus, as the supersonic compressible flow approaches a constriction, and the streamlines converge, velocity decreases and static pressure increases. Continuity of mass flow is maintained by the increase in flow density which accompanies the decrease in velocity. As the supersonic compressible flow enters a diverging section of the tube, velocity increases, static pressure decreases, and density decreases to accommodate the condition of continuity. The previous comparison points out three significant differences between supersonic compressible and subsonic incompressible flow. A. Compressible flow includes the additional variable of flow density. B. Convergence of flow causes expansion of incompressible flow, but compression of compressible flow. C. Divergence of flow causes compression of incompressible flow, but expansion of compressible flow. Typical supersonic flow patterns. When supersonic flow is clearly established, all changes in velocity, pressure, density, flow direction, etc., take place quite suddenly and in relatively confined areas. The areas of flow change are generally distinct, and the phenomena are referred to as wave formations. All compression waves occur suddenly and are wasteful of energy. Hence, the compression waves are distinguished by the sudden shock type of behavior. All expansion waves are not so sudden in their occurrence and are not wasteful of energy like the compression shock waves. Various types of waves can occur in supersonic flow, and the nature of the wave formed depends upon the airstream, and the shape of the object causing the flow change. Essentially, there are three fundamental types of waves formed in supersonic flow. 1. The oblique shock wave, compression. 2. The normal shock wave, compression. 3. The expansion wave, no shock. Oblique shock wave. Consider the case where a supersonic airstream is turned into the preceding airflow. Such would be the case of a supersonic flow into a corner, as shown in figure 3.3. A supersonic airstream passing through the oblique shock wave will experience these changes. 1. The airstream is slowed down, the velocity and Mach number behind the wave are reduced, but the flow is still supersonic. 2. The flow direction is changed to flow along the surface. 3. The static pressure of the airstream behind the wave is increased. 4. The density of the airstream behind the wave is increased. 5. Some of the available energy of the airstream, indicated by the sum of dynamic and static pressure, is dissipated and turned into unavailable heat energy. Hence, the shock wave is wasteful of energy. A typical case of oblique shock wave formation is that of a wedge pointed into a supersonic airstream. The oblique shock wave will form on each surface of the wedge, and the inclination of the shock wave will be a function of the free stream Mach number and the wedge angle. As the free stream Mach number increases, the shockwave angle decreases. As the wedge angle increases, the shockwave angle increases, and, if the wedge angle is increased to some critical amount, the shockwave will detach from the leading edge of the wedge. It is important to note that detachment of the shockwave will produce subsonic flow immediately after the central portion of the shockwave. Figure 3.4 illustrates these typical flow patterns and the effect of Mach number and wedge angle. The previous flow across a wedge in a supersonic airstream would allow flow in 2 dimensions. If a cone were placed in a supersonic airstream, the airflow would occur in 3 dimensions, and there would be some noticeable differences in flow characteristics. 3-dimensional flow for the same Mach number and flow direction change would produce a weaker shockwave with less change in pressure and density. Also, this conical wave formation allows changes in airflow that continue to occur past the wave front, and the wave strength varies with distance away from the surface. Figure 3.5 depicts the typical 3-dimensional flow past a cone. Oblique shock waves can be reflected like any pressure wave, and this effect is shown in Figure 3.5. This reflection appears logical and necessary, since the original wave changes the flow direction toward the wall, and the reflected wave creates the subsequent flow change to cause the flow to remain parallel to the wall surface. This reflection phenomenon places definite restrictions on the size of a model in a wind tunnel, since a wave reflected back to the model would cause a pressure distribution not typical of free flight. Normal shock wave. If a blunt-nosed object is placed in a supersonic airstream, the shock wave which is formed will be detached from the leading edge. This detached wave also occurs when a wedge or cone angle exceeds some critical value. Whenever the shock wave forms perpendicular to the upstream flow, the shock wave is termed a normal shock wave, and the flow immediately behind the wave is subsonic. Any relatively blunt object in a supersonic airstream will form a normal shock wave immediately ahead of the leading edge, slowing the airstream to subsonic so the airstream may feel the presence of the blunt nose and flow around it. Once past the blunt nose, the airstream may remain subsonic or accelerate back to supersonic, depending on the shape of the nose and the Mach number of the free stream. In addition to the formation of normal shock waves described above, this same type of wave may be formed in an entirely different manner when there is no object in the supersonic airstream. It is particular that whenever a supersonic airstream is slowed to subsonic without a change in direction, a normal shock wave will form as a boundary between the supersonic and subsonic regions. This is an important fact, since aircraft usually encounter some compressibility effects before the flight speed is sonic. Figure 3.6 illustrates the manner in which an airfoil at high subsonic speeds has local flow velocities which are supersonic. As the local supersonic flow moves aft, a normal shock wave forms, slowing the flow to subsonic. The transition of flow from subsonic to supersonic is smooth, and is not accompanied by shock waves if the transition is made gradually with a smooth surface. The transition of flow from supersonic to subsonic without direction change always forms a normal shock wave. A supersonic airstream passing through a normal shock wave will experience these changes. 1. The airstream is slowed to subsonic. The local Mach number behind the wave is approximately equal to the reciprocal of the Mach number ahead of the wave. E.g., if Mach number ahead of the wave is 1.25, the Mach number of the flow behind the wave is approximately 0.80. 2. The airflow direction immediately behind the wave is unchanged. 3. The static pressure of the airstream behind the wave is increased greatly. 4. The density of the airstream behind the wave is increased greatly. 5. The energy of the airstream, indicated by total pressure, dynamic plus static, is greatly reduced. The normal shock wave is very wasteful of energy. Expansion wave. If a supersonic airstream were turned away from the preceding flow, an expansion wave would form. The flow around a corner, shown in Figure 3.7, will not cause sharp sudden changes in the airflow except at the corner itself, and thus is not actually a shock wave. A supersonic airstream passing through an expansion wave will experience these changes. 1. The airstream is accelerated, the velocity and Mach number behind the wave are greater. 2. The flow direction is changed to flow along the surface provided separation does not occur. 3. The static pressure of the airstream behind the wave is decreased. 4. The density of the airstream behind the wave is decreased. 5. Since the flow changes in a rather gradual manner, there is no shock and no loss of energy in the airstream. The expansion wave does not dissipate airstream energy. The expansion wave in 3 dimensions is a slightly different case, and the principal difference is the tendency for the static pressure to continue to increase past the wave. The following table is provided to summarize the characteristics of the 3 principal wave forms encountered with supersonic flow. Sections in supersonic flow. In order to appreciate the effect of these various wave forms on the aerodynamic characteristics in supersonic flow, inspect Figure 3.8. Parts A and B show the wave pattern and resulting pressure distribution for a thin flat plate at a positive angle of attack. The airstream moving over the upper surface passes through an expansion wave at the leading edge, and then an oblique shock wave at the trailing edge. Thus, a uniform suction pressure exists over the upper surface. The airstream moving underneath the flat plate passes through an oblique shock wave at the leading edge, then an expansion wave at the trailing edge. This produces a uniform positive pressure on the underside of the section. This distribution of pressure on the surface will produce a net lift and incur a subsequent drag due to lift from the inclination of the resultant lift from a perpendicular to the free stream. Parts C and D of Figure 3.8 show the wave pattern and resulting pressure distribution for a double wedge airfoil at 0 lift. The airstream moving over the surface passes through an oblique shock, an expansion wave, and another oblique shock. The resulting pressure distribution on the surfaces produces no net lift, but the increased pressure on the forward half of the chord along with the decreased pressure on the aft half of the chord produce a wave drag. This wave drag is caused by the components of pressure forces which are parallel to the free stream direction. The wave drag is in addition to the drag due to friction, separation, lift, etc., and can be a very considerable part of the total drag at high supersonic speeds. Parts E and F of Figure 3.8 illustrate the wave pattern and resulting pressure distribution for the double wedge airfoil at a small positive angle of attack. The net pressure distribution produces an inclined lift with drag due to lift, which is in addition to the wave drag at 0 lift. Part G of Figure 3.8 shows the wave pattern for a circular arc airfoil. After the airflow traverses the oblique shock wave at the leading edge, the airflow undergoes a gradual but continual expansion until the trailing edge shock wave is encountered. Part H of Figure 3.8 illustrates the wave pattern on a conventional blunt nose airfoil in supersonic flow. When the nose is blunt, the wave must detach and become a normal shock wave immediately ahead of the leading edge. Of course, this wave form produces an area of subsonic airflow at the leading edge with very high pressure and density behind the detached wave. The drawings of Figure 3.8 illustrate the typical patterns of supersonic flow and point out these facts concerning aerodynamic surfaces in 2-dimensional supersonic flow. 1. All changes in velocity, pressure, density, and flow direction will take place quite suddenly through the various wave forms. The shape of the object and the required flow direction change dictate the type and strength of the wave formed. 2. As always, lift results from the distribution of pressure on a surface and is the net force perpendicular to the free stream direction. Any component of the lift in a direction parallel to the wind stream will be drag due to lift. 3. In supersonic flight, the zero lift drag of an airfoil of some finite thickness will include a wave drag. The thickness of the airfoil will have an extremely powerful effect on this wave drag, since the wave drag varies as the square of the thickness ratio. If the thickness is reduced 50%, the wave drag is reduced 75%. The leading edges of supersonic shapes must be sharp, or the wave formed at the leading edge will be a strong detached shock wave. 4. Once the flow on the airfoil is supersonic, the aerodynamic center of the surface will be located approximately at the 50% chord position. As this contrasts with the subsonic location for the aerodynamic center of the 25% chord position, significant changes in aerodynamic trim and stability may be encountered in transonic flight. Configuration effects. Transonic and supersonic flight. Any object in subsonic flight which has some finite thickness or is producing lift will have local velocities on the surface which are greater than the free stream velocity. Hence, compressibility effects can be expected to occur at flight speeds less than the speed of sound. The transonic regime of flight provides the opportunity for mixed subsonic and supersonic flow and accounts for the first significant effects of compressibility. Consider a conventional airfoil shape as shown in Figure 3.9. If this airfoil is at a flight Mach number of 0.50 and a slight positive angle of attack, the maximum local velocity on the surface will be greater than the flight speed, but most likely less than sonic speed. Assume that an increase in flight Mach number to 0.72 would produce the first evidence of local sonic flow. This condition of flight would be the highest flight speed possible without supersonic flow and would be termed the critical Mach number. Thus, critical Mach number is the boundary between subsonic and transonic flight and is an important point of reference for all compressibility effects encountered in transonic flight. By definition, critical Mach number is the freestream Mach number which produces first evidence of local sonic flow. Therefore, shock waves, buffet, airflow separation, etc., take place above critical Mach number. As critical Mach number is exceeded, an area of supersonic airflow is created, and a normal shock wave forms as the boundary between the supersonic flow and the subsonic flow on the aft portion of the airfoil surface. The acceleration of the airflow from subsonic to supersonic is smooth and unaccompanied by shock waves if the surface is smooth, and the transition gradual. However, the transition of airflow from supersonic to subsonic is always accompanied by a shock wave and, when there is no change in direction of the airflow, the wave form is a normal shock wave. Recall that one of the principal effects of the normal shock wave is to produce a large increase in the static pressure of the airstream behind the wave. If the shock wave is strong, the boundary layer may not have sufficient kinetic energy to withstand the large, adverse pressure gradient, and separation will occur. At speeds only slightly beyond critical Mach number, the shock wave formed is not strong enough to cause separation or any noticeable change in the aerodynamic force coefficients. However, an increase in speed above critical Mach number sufficient to form a strong shock wave can cause separation of the boundary layer and produce sudden changes in the aerodynamic force coefficients. Such a flow condition is shown in Figure 3.9 by the flow pattern for Mach 0.77. Notice that a further increase in Mach number to 0.82 can enlarge the supersonic area on the upper surface and form an additional area of supersonic flow and normal shock wave on the lower surface. As the flight speed approaches the speed of sound, the areas of supersonic flow enlarge, and the shock waves move nearer the trailing edge. The boundary layer may remain separated or may reattach depending much upon the airfoil shape and angle of attack. When the flight speed exceeds the speed of sound, the bow wave forms at the leading edge, and this typical flow pattern is illustrated in Figure 3.9 by the drawing for Mach 1.05. If the speed is increased to some higher supersonic value, all oblique portions of the waves incline more greatly, and the detached normal shock portion of the bow wave moves closer to the leading edge. Of course, all components of the aircraft are affected by compressibility in a manner somewhat similar to that of the basic airfoil. The tail, fuselage, nacelles, canopy, etc., and the effect of the interference between the various surfaces of the aircraft must be considered. Force divergence. The airflow separation induced by shock wave formation can create significant variations in the aerodynamic force coefficients. When the free stream speed is greater than the critical Mach number, some typical effects on an airfoil section are as follows. 1. An increase in the section drag coefficient for a given section lift coefficient. 2. A decrease in section lift coefficient for a given section angle of attack. 3. A change in section pitching moment coefficient. A reference point is usually taken by a plot of drag coefficient versus Mach number for a constant lift coefficient. Such a graph is shown in Figure 3.10. The Mach number which produces a sharp change in the drag coefficient is termed the force divergence Mach number and, for most airfoils, usually exceeds the critical Mach number at least 5 to 10%. This condition is also referred to as the drag divergence or drag rise. Phenomena of transonic flight. Associated with the drag rise are buffet, trim, and stability changes, and a decrease in control surface effectiveness. Conventional aileron, rudder, and elevator surfaces subjected to this high-frequency buffet may buzz, and changes in hinge moments may produce undesirable control forces. Of course, if the buffet is quite severe and prolonged, structural damage may occur if this operation is in violation of operating limitations. When airflow separation occurs on the wing due to shock wave formation, there will be a loss of lift and subsequent loss of downwash aft of the affected area. If the wings shock unevenly due to physical shape differences or sideslip, a rolling moment will be created in the direction of the initial loss of lift and contribute to control difficulty, wing drop. If the shock-induced separation occurs symmetrically near the wing root, a decrease in downwash behind this area is a corollary of the loss of lift. A decrease in downwash on the horizontal tail will create a diving moment, and the aircraft will tuck under. If these conditions occur on a swept-wing planform, the wing center of pressure shift contributes to the trim chong. Root shock first moves the wing center of pressure aft and adds to the diving moment. Shock formation at the wing tips first moves the center of pressure forward, and the resulting climbing moment and tail downwash change can contribute to pitch up. Since most of the difficulties of transonic flight are associated with shockwave-induced flow separation, any means of delaying or alleviating the shock-induced separation will improve the aerodynamic characteristics. An aircraft configuration may utilize thin surfaces of low aspect ratio with sweepback to delay and reduce the magnitude of transonic force divergence. In addition, various methods of boundary layer control, high lift devices, vortex generators, etc., may be applied to improve transonic characteristics. For example, the application of vortex generators to a surface can produce higher local surface velocities and increase the kinetic energy of the boundary layer. Thus, a more severe pressure gradient, stronger shockwave, will be necessary to produce airflow separation. Once the configuration of a transonic aircraft is fixed, the pilot must respect the effective angle of attack and altitude. The local flow velocities on any upper surface increase with an increase in angle of attack. Hence, local sonic flow and subsequent shockwave formation can occur at lower freestream Mach numbers. A pilot must appreciate this reduction of force divergence Mach number with lift coefficient, since maneuvers at high speed may produce compressibility effects which may not be encountered in unaccelerated flight. The effect of altitude is important, since the magnitude of any force or moment change due to compressibility will depend upon the dynamic pressure of the airstream. Compressibility effects encountered at high altitude and low dynamic pressure may be of little consequence in the operation of a transonic aircraft. However, the same compressibility effects encountered at low altitudes and high dynamic pressures will create greater trim changes, heavier buffet, etc., and perhaps transonic flight restrictions which are of principal interest only to low altitude. Phenomena of supersonic flight. While many of the particular effects of supersonic flight will be presented in detail in later discussion, many general effects may be anticipated. The airplane configuration must have aerodynamic shapes which will have low drag and compressible flow. Generally, this will require airfoil sections of low thickness ratio and sharp leading edges, and body shapes of high fineness ratio to minimize the supersonic wave drag. Because of the aft movement of the aerodynamic center with supersonic flow, the increase in static longitudinal stability will demand effective, powerful control surfaces to achieve adequate controllability for supersonic maneuvering. As a corollary of supersonic flight, the shockwave formation on the airplane may create special problems outside the immediate vicinity of the airplane surfaces. While the shock waves a great distance away from the airplane can be quite weak, the pressure waves can be of sufficient magnitude to create an audible disturbance. Thus, sonic booms will be a simple consequence of supersonic flight. The aircraft power plants for supersonic flight must be of relatively high thrust output. Also, in many cases, it may be necessary to provide the air-breathing power plant with special inlet configurations which will slow the airflow to subsonic prior to reaching the compressor face or combustion chamber. Aerodynamic heating of supersonic flight can provide critical inlet temperatures for the gas turbine engine as well as critical structural temperatures. The density variations in airflow may be shown by certain optical techniques. Schlieren photographs and shadowgraphs can define the various wave patterns and their effect on the airflow. The Schlieren photographs presented in Figure 3.11 define the flow conditions on an aircraft in supersonic flight. Transonic and supersonic configurations. Aircraft configurations developed for high-speed flight will have significant differences in shape and planform when compared with aircraft designed for low-speed flight. One of the outstanding differences will be in the selection of airfoil profiles for transonic or supersonic flight. Airfoil sections. It should be obvious that airfoils for high-speed subsonic flight should have high critical Mach numbers, since critical Mach number defines the lower limit for shockwave formation and subsequent force divergence. An additional complication to airfoil selection in this speed range is that the airfoil should have a high maximum lift coefficient and sufficient thickness to allow application of high lift devices. Otherwise, an excessive wing area would be required to provide maneuverability and reasonable takeoff and landing speeds. However, if high-speed flight is the primary consideration, the airfoil must be chosen to have the highest practical critical Mach number. Critical Mach number has been defined as the flight Mach number which produces the first evidence of local sonic flow. Thus, the airfoil shape and lift coefficient which determine the pressure and velocity distribution will have a profound effect on critical Mach number. Conventional, low-speed airfoil shapes have relatively poor compressibility characteristics because of the high local velocities near the leading edge. These high local velocities are inevitable if both the maximum thickness and camber are well forward on the chord. An improvement of the compressibility characteristics can be obtained by moving the points of maximum camber and thickness aft on the chord. This would distribute the pressure and velocity more evenly along the chord, and produce a lower peak velocity for the same lift coefficient. Fortunately, the airfoil shape to provide extensive laminar flow and low profile drag in low speed, subsonic flight will provide a pressure distribution which is favorable for high-speed flight. Figure 3.12 illustrates the pressure distributions and variation of critical Mach number with lift coefficient for a conventional low-speed airfoil and a high-speed section. In order to obtain a high critical Mach number from an airfoil at some low lift coefficient, the section must have a. Low thickness ratio. The point of maximum thickness should be aft to smooth the pressure distribution. b. Low camber. The mean camber line should be shaped to help minimize the local velocity peaks. In addition, the higher the required lift coefficient, the lower the critical Mach number, and more camber is required of the airfoil. If supersonic flight is a possibility, the thickness ratio and leading edge radius must be small to decrease wave drag. Figure 3.13 shows the flow patterns for two basic supersonic airfoil sections and provides the approximate equations for lift, drag, and lift curve slope. Since the wave drag is the only factor of difference between the two airfoil sections, notice the configuration factors which affect the wave drag. For the same thickness ratio, the circular arc airfoil would have a larger wedge angle formed between the upper and lower surfaces at the leading edge. At the same flight Mach number, the larger angle at the leading edge would form the stronger shock wave at the nose and cause a greater pressure change on the circular arc airfoil. This same principle applies when investigating the effect of airfoil thickness. Notice that the wave drag coefficients for both airfoils vary as the square of the thickness ratio, e.g., if the thickness ratio were doubled, the wave drag coefficient would be 4 times as great. If the thickness were increased, the airflow at the leading edge will experience a greater change in direction, and a stronger shock wave will be formed. This powerful variation of wave drag with thickness ratio necessitates the use of very thin airfoils with sharp leading edges for supersonic flight. An additional consideration is that thin airfoil sections favor the use of low aspect ratios and high taper to obtain lightweight structures and preserve stiffness and rigidity. The parameter, square root of m squared minus 1, appears in the denominator of each of the equations for the aerodynamic coefficients, and indicates a decrease in each of these coefficients with an increase in Mach number. Essentially, this means that any aerodynamic surface becomes less sensitive to changes in angle of attack at higher Mach numbers. The decrease in lift curve slope with Mach number has tremendous implications in the stability and control of high-speed aircraft. The vertical tail becomes less sensitive to angles of sideslip, and the directional stability of the aircraft will deteriorate with Mach number. The horizontal tail of the airplane experiences the same general effect and contributes less damping to longitudinal pitching oscillations. These effects can become so significant at high Mach numbers that the aircraft might require complete synthetic stabilization. Planform effects. The development of surfaces for high speed involves consideration of many items in addition to the airfoil sections. Taper, aspect ratio, and sweepback can produce major effects on the aerodynamic characteristics of a surface in high-speed flight. Sweepback produces an unusual effect on the high-speed characteristics of a surface and has its basis in a very fundamental concept of aerodynamics. A grossly simplified method of visualizing the effect of sweepback is shown in Figure 3.14. The swept wing shown has the streamwise velocity broken down to a component of velocity perpendicular to the leading edge and a component parallel to the leading edge. The component of speed perpendicular to the leading edge is less than the freestream speed, by the cosine of the sweep angle, and it is this velocity component which determines the magnitude of the pressure distribution. The component of speed parallel to the leading edge could be visualized as moving across constant sections, and in doing so, does not contribute to the pressure distribution on the swept wing. Hence, sweep of a surface produces a beneficial effect in high-speed flight, since higher flight speeds may be obtained before components of speed perpendicular to the leading edge produce critical conditions on the wing. This is one of the most important advantages of sweep, since there is an increase in critical Mach number, force divergence Mach number, and the Mach number at which the drag rise will peak. In other words, sweep will delay the onset of compressibility effects. Generally, the effect of wing sweep will apply to either sweep back or sweep forward. While the swept forward wing has been used in rare instances, the aeroelastic instability of such a wing creates such a problem that sweep back is more practical for ordinary applications. In addition to the delay of the onset of compressibility effects, sweep back will reduce the magnitude of the changes in force coefficients due to compressibility. Since the component of velocity perpendicular to the leading edge is less than the free stream velocity, the magnitude of all pressure forces on the wing will be reduced, approximately by the square of the cosine of the sweep angle. Since compressibility force divergence occurs due to changes in pressure distribution, the use of sweep back will soften the force divergence. This effect is illustrated by the graph of figure 3.14, which shows the typical variation of drag coefficient with Mach number for various sweep back angles. The straight wing shown begins drag rise at Mach 0.70, reaches a peak near Mach 1.0, and begins a continual drop past Mach 1. Note that the use of sweep back then delays the drag rise to some higher Mach number and reduces the magnitude of the drag rise. In view of the preceding discussion, sweep back will have the following principal advantages. 1. Sweep back will delay the onset of all compressibility effects. Critical Mach number and force divergence Mach number will increase, since the velocity component affecting the pressure distribution is less than the free stream velocity. Also, the peak of drag rise is delayed to some higher supersonic speed, approximately the speed which produces sonic flow perpendicular to the leading edge. Various sweeps applied to wings of moderate aspect ratio will produce these approximate effects in transonic flight. Sweep angle, 0 degrees, 0% increase in critical Mach number. 0% increase in drag peak Mach number. Sweep angle, 15 degrees, 2% increase in critical Mach number. 4% increase in drag peak Mach number. Sweep angle, 30 degrees, 8% increase in critical Mach number. 15% increase in drag peak Mach number. Sweep angle, 45 degrees. 20% increase in critical Mach number. 41% increase in drag peak Mach number. Sweep angle, 60 degrees, 41% increase in critical Mach number. 100% increase in drag peak Mach number. 2. Sweep back will reduce the magnitude of change in the aerodynamic force coefficients due to compressibility. Any change in drag, lift, or moment coefficients will be reduced by the use of sweep back. Various sweep angles applied to wings of moderate aspect ratio will produce these approximate effects in transonic flight. Sweep angle, 0 degrees, 0% reduction in drag rise. 0% reduction in loss of capital CL max. Sweep angle, 15 degrees, 5% reduction in drag rise. 3% reduction in loss of capital CL max. Sweep angle, 30 degrees, 15% reduction in drag rise. 13% reduction in loss of capital CL max. Sweep angle, 45 degrees, 35% reduction in drag rise. 30% reduction in loss of capital CL max. Sweep angle, 60 degrees, 60% reduction in drag rise. 50% reduction in loss of capital CL max. These advantages of drag reduction and preservation of the transonic maximum lift coefficient are illustrated in figure 3.14. Thus, the use of sweep back on a transonic aircraft will reduce and delay the drag rise, and preserve the maneuverability of the aircraft in transonic flight. It should be noted that a small amount of sweep back produces very little benefit. If sweep back is to be used at all, at least 30 degrees to 35 degrees must be used to produce any significant benefit. Also note from figure 3.14 that the amount of sweep back required to delay drag rise in supersonic flight is very large, e.g., more than 60 degrees necessary at Mach 2.0. By comparison of the drag curves at high Mach numbers, it will be appreciated that extremely high, and possibly impractical, sweep back is necessary to delay drag rise, and that the lowest drag is obtained with zero sweep back. Therefore, the planform of a wing designed to operate continuously at high Mach numbers will tend to be very thin, low aspect ratio, and unswept. An immediate conclusion is that sweep back is a device of greatest application in the regime of transonic flight. A few of the less significant advantages of sweepback are as follows. 1. The wing lift curve slope is reduced for a given aspect ratio. This is illustrated by the lift curve comparison of figure 3.15 for the straight and swept wing. Any reduction of lift curve slope implies the wing is less sensitive to changes in angle of attack. This is a beneficial effect only when the effect of gusts and turbulence is considered. Since the swept wing has the lower lift curve slope, it will be less sensitive to gusts and experience less bump due to gust for a given aspect ratio and wing loading. This is a consideration particular to the aircraft whose structural design shows a predominating effect of the gust load spectrum, e.g., transport, cargo, and patrol types. 2. Divergence of a surface is an aeroelastic problem which can occur at high dynamic pressures. Combined bending and twisting deflections interact with aerodynamic forces to produce sudden failure of the surface at high speeds. Sweep forward will aggravate this situation by leading the wing into the wind stream, and tends to lower the divergence speed. On the other hand, sweepback tends to stabilize the surface by trailing and tends to raise the divergence speed. By this tendency, sweepback may be beneficial in preventing divergence within the anticipated speed range. 3. Sweepback contributes slightly to the static directional or weathercock stability of an aircraft. This effect may be appreciated by inspection of figure 3.13, which shows the swept wing in a yaw or side slip. The wing into the wind has less sweep and a slight increase in drag, the wing away from the wind has more sweep and less drag. The net effect of these force changes is to produce a yawing moment, tending to return the nose into the relative wind. This directional stability contribution is usually small and of importance in tailless aircraft only. 4. Sweepback contributes to lateral stability in the same sense as dihedral. When the swept wing aircraft is placed in a side slip, the wing into the wind experiences an increase in lift, since the sweep is less, and the wing away from the wind produces less lift, since the sweep is greater. As shown in figure 3.15, the swept wing aircraft in a side slip experiences lift changes and a subsequent rolling moment which tends to right the aircraft. This lateral stability contribution depends on the sweepback and the lift coefficient of the wing. A highly swept wing operating at high lift coefficient usually experiences such an excess of this lateral stability contribution that adequate controllability may be a significant problem. As shown, the swept wing has certain important advantages. However, the use of sweepback produces certain inevitable disadvantages which are important from the standpoint of both airplane design and flight operations. The most important of these disadvantages are as follows. 1. When sweepback is combined with taper, there is an extremely powerful tendency for the wing to stall tip first. This pattern of stall is very undesirable, since there would be little stall warning, a serious reduction in lateral control effectiveness, and the forward shift of the center of pressure would contribute to a nose-up moment, pitch-up or stick force lightning. Taper has its own effect of producing higher local lift coefficients toward the tip, and one of the effects of sweepback is very similar. All outboard wing sections are affected by the upwash of the preceding inboard sections, and the lift distribution resulting from sweepback alone is similar to that of high taper. An additional effect is the tendency to develop a strong spanwise flow of the boundary layer toward the tip when the wing is at high lift coefficients. This spanwise flow produces a relatively low energy boundary layer near the tip which can be easily separated. The combined effect of taper and sweep present a considerable problem of tip stall, and this is illustrated by the flow patterns of figure 3.16. Design for high-speed performance may dictate high sweepback, while structural efficiency may demand a highly tapered planform. When such is the case, the wing may require extensive aerodynamic tailoring to provide a suitable stall pattern and a lift distribution at cruise condition which reduces drag due to lift. Washout of the tip, variation of section camber throughout span, flow fences, slats, leading edge extension, etc., are typical devices used to modify the stall pattern and minimize drag due to lift at cruise condition. 2. As shown by the lift curve of figure 3.15, the use of sweepback will reduce the lift curve slope and the subsonic maximum lift coefficient. It is important to note this case is definitely subsonic, since sweepback may be used to improve the transonic maneuvering capability. Various sweep angles applied to wings of moderate aspect ratio produce these approximate effects on the subsonic lift characteristics. Sweep angle, 0 degrees, 0% reduction of subsonic maximum lift coefficient and lift curve slope. Sweep angle, 15 degrees, 4% reduction of subsonic maximum lift coefficient and lift curve slope. Sweep angle, 30 degrees, 14% reduction of subsonic maximum lift coefficient and lift curve slope. Sweep angle, 45 degrees, 30% reduction of subsonic maximum lift coefficient and lift curve slope. Sweep angle, 60 degrees, 50% reduction of subsonic maximum lift coefficient and lift curve slope. The reduction of the low speed maximum lift coefficient, which is in addition to that lost due to tip stall, has very important implications in design. If wing loading is not reduced, stall speeds increase, and subsonic maneuverability decreases. On the other hand, if wing loading is reduced, the increase in wing surface area may reduce the anticipated benefit of sweepback in the transonic flight regime. Since the requirements of performance predominate, certain increases of stall speeds, takeoff speeds, and landing speeds usually will be accepted. While the reduction of lift curve slope may be an advantage for gust considerations, the reduced sensitivity to changes in angle of attack has certain undesirable effects in subsonic flight. The reduced wing lift curve slope tends to increase maximum lift angles of attack and complicate the problem of landing gear design and cockpit visibility. Also, the lower lift curve slope would reduce the contribution to stability of a given tail surface area. 3. The use of sweepback will reduce the effectiveness of trailing edge control surfaces and high lift devices. A typical example of this effect is the application of a single slotted flap over the inboard 60% span to both a straight wing and a wing with 35-degree sweepback. The flap applied to the straight wing produces an increase in maximum lift coefficient of approximately 50%. The same type flap applied to the swept wing produces an increase in maximum lift coefficient of approximately 20%. To produce some reasonable maximum lift coefficient, a swept wing may require unsweeping the flap hinge line, application of leading-edge high-lift devices such as slots or slats, and possibly boundary layer control. 4. As described previously, sweepback contributes to lateral stability by producing stable rolling moments with side slip. The lateral stability contribution of sweepback varies with the amount of wing sweepback and wing lift coefficient. Large sweepback and high lift coefficients produce large contributions to lateral stability. While stability is desirable, any excess of stability will reduce controllability. For the majority of airplane configurations, high lateral stability is neither necessary nor desirable, but adequate control in roll is absolutely necessary for good flying qualities. An excess of lateral stability from sweepback can aggravate Dutch roll problems and produce marginal control during crosswind takeoff and landing where the aircraft must move in a controlled side slip. Therefore, it is not unusual to find swept-wing aircraft with negative dihedral and lateral control devices designed principally to meet crosswind takeoff and landing requirements. 5. The structural complexity and aeroelastic problems created by sweepback are of great importance. First, there is the effect, shown in Figure 3.17, that a swept wing has a greater structural span than a straight wing of the same area and aspect ratio. This effect increases wing structural weight, since greater bending and shear material must be distributed in the wing to produce the same design strength. An additional problem is created near the wing root and carry-through structure due to the large twisting loads and the tendency of the bending stress distribution to concentrate toward the trailing edge. Also shown in Figure 3.17 is the influence of wing deflection on the spanwise lift distribution. Wing bending produces tip rotation, which tends to unload the tip and move the center of pressure forward. Thus, the same effect which tends to allay divergence can make an undesirable contribution to longitudinal stability. Effect of aspect ratio and tip shape. In addition to wing sweep, planform properties such as aspect ratio and tip shape can produce significant effects on the aerodynamic characteristics at high speeds. There is no particular effect of aspect ratio on critical Mach number at high or medium aspect ratios. The aspect ratio must be less than 4 or 5 to produce any apparent change in critical Mach number. This effect is shown for a typical 9% thick symmetrical airfoil in the graph of Figure 3.18. Note that very low aspect ratios are required to cause a significant increase in critical Mach number. Very low aspect ratios create the extremes of three-dimensional flow and a subsequent increase in free stream speed to create local sonic flow. Actually, the extremely low aspect ratios required to produce high critical Mach numbers are not too practical. Generally, the advantage of low aspect ratios must be combined with sweepback and high-speed airfoil sections. The thin rectangular wing in supersonic flow illustrates several important facts. As shown in Figure 3.18, Mach cones form at the tips of the rectangular wing and affect the pressure distribution on the area within the cone. The vortex develops within the tip cone due to the pressure differential, and the resulting average pressure on the area within the cone is approximately 1/2 the pressure between the cones. Three-dimensional flow on the wing is then confined to the area within the tip cones, while the area between the cones experiences pure two-dimensional flow. It is important to realize that the three-dimensional flow on the rectangular wing in supersonic flight differs greatly from that of subsonic flight. A wing of finite aspect ratio in subsonic flight experiences a three-dimensional flow, which includes the tip vortices, downwash behind the wing, upwash ahead of the wing, and local induced velocities along the span. Recall that the local induced velocities along the span of the wing would incline the section lift-aft relative to the free stream and result in induced drag. Such a flow condition cannot be directly correlated with the wing in supersonic flow. The flow pattern for the rectangular wing of Figure 3.18 demonstrates that the three-dimensional flow is confined to the tip, and pure two-dimensional flow exists on the wing area between the tip cones. If the wing tips were to be raked outside the tip cones, the entire wing flow would correspond to the two-dimensional, or section, conditions. Therefore, for the wing in supersonic flow, no upwash exists ahead of the wing, three-dimensional effects are confined to the tip cones, and no local induced velocities occur along the span between the tip cones. The supersonic drag due to lift is a function of the section and angle of attack, while the subsonic induced drag is a function of lift coefficient and aspect ratio. This comparison makes it obvious that supersonic flight does not demand the use of high aspect ratio planforms typical of low-speed aircraft. In fact, low aspect ratios and high taper are favorable from the standpoint of structural considerations if very thin sections are used to minimize wave drag. If sweepback is applied to the supersonic wing, the pressure distribution will be affected by the location of the Mach cone with respect to the leading edge. Figure 3.19 illustrates the pressure distribution for the delta wing planform in supersonic flight, with the leading edge behind or ahead of the Mach cone. When the leading edge is behind the Mach cone, the components of velocity perpendicular to the leading edge are still subsonic, even though the free stream flow is supersonic, and the resulting pressure distribution will greatly resemble the subsonic pressure distribution for such a planform. Tailoring the leading edge shape and camber can minimize the components of the high leading edge suction pressure, which are inclined in the drag direction, and the drag due to lift can be reduced. If the leading edge is ahead of the Mach cone, the flow over this area will correspond to the two-dimensional supersonic flow and produce constant pressure for that portion of the surface between the leading edge and the Mach cone. Control surfaces. The design of control surfaces for transonic and supersonic flight involves many important considerations. This fact is illustrated by the typical transonic and supersonic flow patterns of Figure 3.19. Trailing edge control surfaces can be affected adversely by the shock waves formed in flight above critical Mach number. If the airflow is separated by the shock wave, the resulting buffet of the control surface can be very objectionable. In addition to the buffet of the surface, the change in the pressure distribution due to separation and the shock wave location can create very large changes in control surface hinge moments. Such large changes in hinge moments create very undesirable control forces and present the need for an irreversible control system. An irreversible control system would employ powerful hydraulic or electric actuators to move the surfaces upon control by the pilot, and the air loads developed on the surface could not feed back to the pilot. Of course, suitable control forces would be synthesized by bungees, Q-springs, bob weights, etc. Transonic and supersonic flight can cause a noticeable reduction in the effectiveness of trailing edge control surfaces. The deflection of a trailing edge control surface at low subsonic speeds alters the pressure distribution on the fixed portion, as well as the movable portion, of the surface. This is true to the extent that a 1-degree deflection of a 40% chord elevator produces a lift change very nearly the equivalent of a 1-degree change in stabilizer setting. However, if supersonic flow exists on the surface, a deflection of the trailing edge control surface cannot influence the pressure distribution in the supersonic area ahead of the movable control surface. This is especially true in high supersonic flight, where supersonic flow exists over the entire chord, and the change in pressure distribution is limited to the area of the control surface. The reduction in effectiveness of the trailing edge control surface at transonic and supersonic speeds necessitates the use of an all-movable surface. Application of the all-movable control surface to the horizontal tail is most usual, since the increase in longitudinal stability in supersonic flight requires a high degree of control effectiveness to achieve required controllability for supersonic maneuvering. Supersonic engine inlets. Air which enters the compressor section of a jet engine or the combustion chamber of a ramjet usually must be slowed to subsonic velocity. This process must be accomplished with the least possible waste of energy. At flight speeds just above the speed of sound, only slight modifications to ordinary subsonic inlet design produce satisfactory performance. However, at supersonic flight speeds, the inlet design must slow the air with the weakest possible series, or combination, of shock waves to minimize energy losses and temperature rise. Figure 3.20 illustrates some of the various forms of supersonic inlets or diffusers. One of the least complicated types of inlet is the simple normal shock type diffuser. This type of inlet employs a single normal shock wave at the inlet with a subsequent internal subsonic compression. At low supersonic Mach numbers, the strength of the normal shock wave is not too great, and this type of inlet is quite practical. At higher supersonic Mach numbers, the single normal shock wave is very strong and causes a great reduction in the total pressure recovered by the inlet. In addition, it is necessary to consider that the wasted energy of the airstream will appear as an additional undesirable rise in temperature of the captured inlet airflow. If the supersonic airstream can be captured, the shock wave formations will be swallowed, and a gradual contraction will reduce the speed to just above sonic. The subsequent diverging flow section can then produce the normal shock wave, which slows the airstream to subsonic. Further expansion continues to slow the air to lower subsonic speeds. This is the convergent-divergent type inlet shown in figure 3.20. If the initial contraction is too extreme for the inlet Mach number, the shock wave formation will not be swallowed and will move out in front of the inlet. The external location of the normal shock wave will produce subsonic flow immediately at the inlet. Since the airstream is suddenly slowed to subsonic through the strong normal shock, a greater loss of airstream energy will occur. Another form of diffuser employs an external oblique shock wave which slows the supersonic airstream before the normal shock occurs. Ideally, the supersonic airstream could be slowed gradually through a series of very weak oblique shock waves to a speed just above sonic velocity. Then, the subsequent normal shock to subsonic could be quite weak. Such a combination of the weakest possible waves would result in the least waste of energy and the highest pressure recovery. The efficiency of various types of diffusers is shown in figure 3.20 that illustrate this principle. An obvious complication of the supersonic inlet is that the optimum shape is variable with inlet flow direction and Mach number. In other words, to derive highest efficiency and stability of operation, the geometry of the inlet would be different at each Mach number and angle of attack of flight. A typical supersonic military aircraft may experience large variations in angle of attack, side slip angle, and flight Mach number during normal operation. These large variations in inlet flow conditions create certain important design considerations. 1. The inlet should provide the highest practical efficiency. The ratio of recovered total pressure to airstream total pressure is an appropriate measure of this efficiency. 2. The inlet should match the demands of the power plant for airflow. The airflow captured by the inlet should match that necessary for engine operation. 3. Operation of the inlet at flight conditions other than the design condition should not cause a noticeable loss of efficiency or excess drag. The operation of the inlet should be stable and not allow buzz conditions, an oscillation of shock location possible during off-design operation. In order to develop a good, stable inlet design, the performance at the design condition may be compromised. A large variation of inlet flow conditions may require special geometric features for the inlet surfaces, or a completely variable geometry inlet design. Supersonic configurations. When all the various components of the supersonic airplane are developed, the most likely general configuration properties will be as follows. 1. The wing will be of low aspect ratio, have noticeable taper, and have sweepback depending on the design speed range. The wing sections will be of low thickness ratio and require sharp leading edges. 2. The fuselage and nacelle will be of high fineness ratio, long and slender. The supersonic pressure distribution may create significant lift and drag, and require consideration of the stability contribution of these surfaces. 3. The tail surfaces will be similar to the wing. Low aspect ratio, tapered, swept, and a thin section with sharp leading edge. The controls will be fully powered and irreversible, with all movable surfaces the most likely configuration. 4. In order to reduce interference drag in transonic and supersonic flight, the gross cross-section of the aircraft may be area-ruled to approach that of some optimum high-speed shape. One of the most important qualities of high-speed configurations will be the low-speed flight characteristics. The low aspect ratio swept-wing planform has the characteristic of high induced drag at low flight speeds. Steep turns, excessively low airspeeds, and steep, power-off approaches can then produce extremely high rates of descent during landing. Sweepback and low aspect ratio can cause severe deterioration of handling qualities at speeds below those recommended for takeoff and landing. On the other hand, thin, swept wings at high wing loading will have relatively high landing speeds. Any excess of this basically high airspeed can create an impossible requirement of brakes, tires, and arresting gear. These characteristics require that the pilot account for the variation of optimum speeds with weight changes and adhere to the procedures and techniques outlined in the flight handbook. Aerodynamic heating. When air flows over any aerodynamic surface, certain reductions in velocity occur with corresponding increases in temperature. The greatest reduction in velocity and increase in temperature will occur at the various stagnation points on the aircraft. Of course, similar changes occur at other points on the aircraft, but these temperatures can be related to the ram temperature rise at the stagnation point. While subsonic flight does not produce temperatures of any real concern, supersonic flight can produce temperatures high enough to be of major importance to the airframe and powerplant structure. The graph of Figure 3.21 illustrates the variation of ram temperature rise with airspeed in the standard atmosphere. The ram temperature rise is independent of altitude and is a function of true airspeed. Actual temperatures would be the sum of the temperature rise and the ambient air temperature. Thus, low-altitude flight at high Mach numbers will produce the highest temperatures. In addition to the effect on the crew member environment, aerodynamic heating creates special problems for the airplane structure and the power plant. The effect of temperature on the short-time strength of three typical structural materials is shown in Figure 3.21. Higher temperatures produce definite reductions in the strength of aluminum alloys, and require the use of titanium alloys, stainless steels, etc., at very high temperatures. Continued exposure at elevated temperatures affects further reductions of strength, and magnifies the problems of creep failure and structural stiffness. The turbojet engine is adversely affected by high compressor inlet air temperatures. Since the thrust output of the turbojet is some function of the fuel flow, high compressor inlet air temperatures reduce the fuel flow that can be used within turbine operating temperature limits. The reduction in performance of the turbojet engines with high compressor inlet air temperatures requires that the inlet design produce the highest practical efficiency and minimize the temperature rise of the air delivered to the compressor face. High flight speeds and compressible flow dictate airplane configurations which are much different from the ordinary subsonic airplane. To achieve safe and efficient operation, the pilot of the modern, high-speed aircraft must understand and appreciate the advantages and disadvantages of the configuration. A knowledge of high-speed aerodynamics will contribute greatly to this understanding.